In this video, we're going to talk about different claw and lift mechanisms used in VEX. And we're going to first start with claw mechanisms. Here we have the V5 standard claw, and I will demonstrate how this mechanism works. So as you can see, the claw, its open state is like this, and it closes. In this particular claw, we have a 3-to-1 gear ratio, as this small gear here is a 12 tooth, and this larger gear that is driving the claw is a 36 tooth gear. So, I mean, a 3-to-1 gear ratio is usually a standard gear ratio that you would use in a claw mechanism like this. Something good about this claw mechanism that utilizes rubber bands at the point where the claw contacts a game element, and that usually allows you to create more friction at that point of contact, and so it grips onto the object better. Something to note, I mean, I'm saying some general things about claws, like a 3-to-1 gear ratio can be good, and putting rubber bands at the ends of your claw clamp can help grab an object more effectively. But generally speaking, competitive teams do not use this standard V5 claw that comes in a kit. Instead, they create their own claws, and well, I have an example here. So for this year's game, for the year this game was, this claw was used, they were clamping on these pieces called mobile goals, which are kind of like a giant oversized cup. I guess you could think of it that way. And how this worked was it just clamped down like this, moved up and down, right? Something you'll note here is that this claw doesn't have any gear ratio, or so it seemed. But what they did was they switched out the internal gear cartridge of their motor to increase torque. They used the red gear cartridge. If you don't know what I'm talking about, well, you can figure it out on the VEX website. That's actually something you should go research, find out more about different motor cartridges and what they mean. So, I mean, for claws, it's not really like any particular pros or cons. You just apply it when you need to. When you need to grab something, you have to use some kind of claw. That's just how it is. And variations, I mean, this is like a basic. These two are just some basic claw examples, but really you design the claw to grab and clamp in a certain way based on what's effective for that year's game. It really varies quite a bit, so there's nothing more I can really say about that. You just have something clamped down, usually by the rotation of a motor. Now, one other way would be to do it with pneumatics, where a piston extends. You know what? Let me go find a file with that as an example. Okay, so in this file, I believe this joint works. So they use, okay, that was a bit weird. Do you work? Yeah, okay, it kind of works. So okay, here they used a pneumatic cylinder that uses pressurized air to extend and retract, and that can move the claw. The joint here is not working perfectly, but because I haven't grounded the tower, but you can see this section of claw going down and going back up. So that's another way you could power your claw mechanisms. Using pneumatics is generally considered to be a more advanced kind of thing, and we, at least as of right now when I'm making this video, we have a limited number of pneumatics in the shop, so you have a really good reason to use it. Try and make your claws with motors. And, well, okay, something to note is that, at least for this year's game, there is a limit of 8 motors that you can use, but you can also use a pneumatic system on top of that. So if you've already used up all 8 of your motors in your design, but you really need to create one additional claw to claw something, yeah, that's when you would use a pneumatics claw. Okay. Okay, so now we're going to be moving on to different lift mechanisms. I'm going to first explain how this 1-bar lift works. So imagine you have your claw attached at the end of this small C channel here, right? And it's pointed at an angle like perpendicular to that surface I clicked on. Okay. I mean, this is pretty basic. Your motor spins and it turns the arm. And now that we're at a different angle, we can see that the claw is pointing in a different direction. It's rotated along with the arm. And in a lot of cases, this might be really annoying because say you had to pick up, say you can only pick up and release an object when the claw's at a certain angle. Well, now that angle's changed, and that might make it more difficult to drop the piece once you picked it up, and let's say you need to drop it off at a high place, then yeah, this may not be the best arm. But sometimes situationally it's a better, it is the arm that you want to use when you're okay with the claw rotating with the arm, or maybe you want that. Okay. Variations, I mean, it's all about the gearing. You try to optimize the gear ratio, so that means making sure your mechanism has enough torque to actually complete the task, but making it as fast as possible. And the lowest gear ratio I've seen that worked for a lift of any kind, really. Okay, well, of a 4-bar, but it probably would be the same for like this 1-bar, is a 10-to-1 gear ratio. And how they did that was they changed the green cartridge in here to a red cartridge to give it the motor a bit more torque, and just used a 5-to-1 gear ratio between gears, between a 60-tooth gear and a 12-tooth gear. And I got to 10-to-1, and the lift generally did work. So I don't know, you have to play around, you have to try different ratios. This is done best by just trying things out and seeing what works for your mechanism, because it depends on like how long this arm is, and also how heavy the object is at the end of the arm that you're carrying, right? That will affect how much torque you actually need to apply in order to lift whatever game element you're dealing with, and it changes by year. All right, so now we're gonna move on to a different arm. This is a linkage, and I mean, I have 3 different linkages here, but there's actually more than that, but I'm just covering the more basic 3. Okay, and so what's special about this? You're about to see. Well, again, let's imagine our claw is on the surface of this 2-by, right? And it's pointing perpendicular to it, and given its current orientation, that would actually be parallel to the ground. Okay, and so we're gonna drive this, and look at that. This end of the arm, where the claw would be attached to, is remaining in the same orientation no matter where you put the arm, right? And this can be very useful. Now, how is this actually being done? You have to make 3 loose joints and 1 driven by the motor. Okay, so we don't count screws in VEX, right? but you have to imagine there's a screw and some kind of nut on the other side, but you don't tighten down this joint so much so that it can freely turn. And that's the same for this joint, okay? And that is also the same for this joint. In this case, we're actually just using an axle. That would probably make it turn a bit smoother, okay? And then this joint down here is the only one being actually driven by the motor, okay? I mean, it's an 84-tooth gear being to 12-tooth gear with a green motor cartridge. And yeah, again, what I said earlier about different ratios, like a 10-to-1 has worked, what I've seen. But like, yeah, you just really need to try it out and see which gear ratio is most optimal for whatever you're trying to accomplish with your arm mechanism. Okay, and I mean, pros of this, you're like, linkages, all what they have in common is that they have this piece at the end stay perpendicular to the ground. Okay, and that lets you usually fashion on some kind of claw at the end of it that is going to remain parallel or perpendicular depending on what you're looking at with your claw to the ground, and so it doesn't change orientation as your arm moves up and down. Okay, so that's a general advantage for all linkages. Now, comparing the different linkages, this one, something it does is you'll see, let's track the end of it, right? It moves in an arc. So that can be okay, but I mean, imagine you pick up a game element down here, right? And maybe you're right up against the wall, and then now you start moving your arm up. Okay, now your arm is moving further forward while it goes up, and then it could hit something. So that's not necessarily a good thing. And maybe you want to pick something up here, and you want to deposit it like from the same distance from the tower, but some ways up. Well, now you would have to drive backwards so you could put it there, right? That's just something to consider, that these linkage arms move in an arc. Generally, it's not going to usually be a problem, but it's something you need to keep in mind. Well, pros of this mechanism, it's simpler than the other ones I'm about to cover. So we're going to move on. This is the 6-bar lift. Okay, again, I'll spin around so you get a chance to check it out. If you'll let me click on this. Okay. Great. So, yeah. Again, this piece at the very end is staying perpendicular to the ground. Okay. Now, what's different about this one? It's a bit more complicated. As you can see, there's more pieces involved, but not too many more. And in this 6-bar, there are 6 bars. 1, 2, 3, 4, 5, and the tower counts as the 6th one. Okay, usually a 6-bar needs a bit more torque than a 4-bar to actually work, but in this CAD, we've just kept the same ratio for the sake of simplicity. Okay, and so why would you ever use a 6-bar over a 4-bar? So, okay, let's take a look at its most extreme points. Okay, it's a 6-bar lets you get a bit more reach than the 4-bar. And how does it accomplish this? So let's go all the way down, right? And this is the stopping point, assuming the green line was the ground. And if you just had a 4-bar extended the whole way, you're tracking where my mouse is going over right now, it would actually be pressing into the ground right now. This wouldn't be physically possible, but it is right now because this is actually a 6-bar. Okay, and then let's go up to a higher state. Again, because it's a 6-bar and not a 4-bar, as I'm tracing my mouse kind of right now, right? It has a tiny bit, it can reach a tiny bit higher because it's a 6-bar. So not too different from a 4-bar, but the con of this con of making a 6-bar is Sometimes you create more friction because you just have more joints in the mechanism, so you need to be careful about that. It's slightly more complicated to use, it's slightly more pieces, but the pros over the 4-bar, yeah, it can be a bit more compact. Like the 4-bar, I will mention that again, this end piece moves in an arc. Okay, and that usually isn't a problem, but something just to keep in mind. So now we got the final basic linkage I'll cover in this video. The double reverse 4-bar. So how does this one work? It's interesting. But first, let me show, then I'll explain. This probably doesn't like doing all the calculations because it moves like this. Okay. What the hell are we looking at, you might wonder. Alright. Well, let's get into it. So, first if I look at it from this angle, well, okay, it did look like the arms crossed there, but if I look at it from this angle, right, you can see it's designed so that mostly the arms are not intersecting when they go up and down. Okay, they're not intersecting when they go up and down. And yeah, that's something you need to keep in mind when making this kind of double reverse 4-bar. But again, how does this actually work? So you have a 4-bar on the bottom, and you have some big gear. In this case, we're using an 84 tooth gear, but a 60 could also work, but it needs to be a gear of decent size usually. And we have a screw here going through the gear into the C channel. Okay, so it's kind of locked this gear's orientation with the C channel. And that's the same case between this gear and this C channel. Okay, and this whole other, and we have a whole other 4-bar on top of this 4-bar at the bottom. Okay, so I'm gonna try to drive this slowly. If you think about it, right, this bottom arm, it goes up a bit, right? And that changes this gear's orientation. As this gear is locked with the arm, now it's turned. Okay, and since this gear is turning at the bottom, the top gear also has to turn. So if I shift this a tiny bit, right, this gear still lined up with that C channel, and it had to turn a tiny bit. Let's see if I can slowly type in values. We start at 0, and if we were to go to 1, okay, it's turning bit by bit. Barely see it. Okay, different teeth are meshing, and that's what drives this top 4-bar. Okay, it makes it also turn while the bottom one is turning. That's how that works. Okay, and well, all right. What are okay for double reverse 4-bar also because you have more weight created by this whole part of it. Okay, and in all the cases we've been ignoring the weight of the claw at the end of it. You need to usually provide more torque than compared to the other linkages that we explored in this video to make it work. Okay, you need to provide more torque because it's heavier. Okay, other pros and cons. So this lift gets a lot, it can reach very high. So it has a lot higher reach compared to other linkages, right? Because it's like we have a 4-bar here, standard 4-bar at the bottom, and then you're almost getting double the height because you have a whole other 4-bar on top of that. So pretty useful in that sense. Another thing is if you look at where the claw attaches at the very end of this, because we have a double reverse 4-bar, it's actually, please stop doing that. It actually moves up and down in a straight line. See, path is straight. Okay, and so it doesn't move in an arc like the other mechanisms, and sometimes this is useful, like you need to move something straight up and down. This is one way to do it. Okay, and what else do we got? the cons of doing this are, well, it's more complicated than the other mechanisms, and simplicity in robotics is usually a good thing. So if you can accomplish a task by using a 4-bar, a normal 4-bar, just use a normal 4-bar. Okay, but there are instances where you need to use a double reverse 4-bar, like taking advantage of this mechanism's super high reach, or needing to make sure that the claw travels only straight up and down and not in an arc. Okay, then yeah, I guess you have to use a double reverse 4-bar. And other problems are just because you have more pieces, sometimes people do not take care in just reducing friction and putting in all the spacers that you need to, okay, to reduce friction. And if you ignore the friction problem, it's going to make the mechanism super inefficient, and it will quickly overheat the motors. That's a problem that teams have experienced when trying to build a double reverse 4-bar. Okay, but that's not to say that it's not usable. You just have to be careful with it and find ways to reduce the friction in the mechanism. Okay, so yeah, that is it for this video on arms and lifts.